Okay, the transformations, there really is just three. A reflection, rotation, translation. A glide reflection is just what it sounds like. A glide is a slide for a translation, and then you reflect it. So if you had a picture, this is an example of what could be a glide reflection. It could slide over here to there and then reflect to there. Okay? So that's what a glide reflection. We didn't do a lot of those, but it could be a rotation. So here it looks exactly the same, so it's a translation. Here it's not a translation, it's not a reflection because the head would be there, so it's got to be a rotation. This one, it's just folded on top of itself, it's upside down, so that's a rotation, a reflection. Here, I don't know why these aren't shaded in, they're supposed to be the same, but this would fold down on top of that, so that's a reflection. The line, if you had to draw it in there, that you'd reflect it over, would be right there. And some of these, if you don't know what it is, you can just do a process elimination. It doesn't look the same, so it's not a translation. It can't fold on top of itself, so it's not a reflection. So it's got to be a rotation. This one just slid down to the right, so it's a translation. Okay, here we've got the actual pictures. Again, we don't need to say how far you moved them or whatnot. You just got to say what it is. So here's the original. It's slid up here. B, C, and A are still in their same positions. So that's just a translation. This one, it's not a translation. It's not a reflection. So it has to be a rotation. And if you did have to describe, it'd be a 90-degree counterclockwise about the origin, but you don't need to. And for this one, quiet. B and C are on the right, B and C are on the right. It's the same, it's just been slid up. So this is just or it's been slid down from here to here. So that's just a translation. Lines of symmetry, that'd be like if you could cut it into two equal pieces that would fold on top of each other. So if it's an equilateral, or if it's a regular polygon, however many sides it has, that's how many lines of symmetry it would have. So a pentagon would have how many? 5. Through each point. Oh, did I miss one? No. Right there. And a rectangle, just 2. So remember now, I think that's it for that, but a circle is infinite, but if you have a flag like this, then it's just 2. You can cut it this way and that way. Okay? Rotational symmetry. Easy as long as you remember what it is. Rotational symmetry is you can turn it a half a turn or less and it looks the same. So, would this have rotational symmetry? Yes. And when it says describe it, that just means how many degrees would you turn it and it would look the same.
90.
There's 4 equal things, so you just take 360 divided by 4 is 90. So it'd be 90 and 180. Remember, you go up to 180. Once you get over, you stop. This one would be yes. It's a hexagon. So every 6th turn, it would look the same. So you take 360 divided by 6 is 60. So 60 degrees, another 6. Shh, quiet, everybody. Another 6 of a turn is 120, and then another 60 degrees would be at 180. So this one has 1, 2, 3, 4, 5, 6, 7, 8. So take 360 divided by 8. 45. So I would have a 45, a 90, a 135, and a 180 degree rotational symmetry. This wheel, there's 1, 2, 3, 4, 5, 6, 7, 8.
Same thing.
So it's the same thing. Now, remember this one, all of them did, but on the test I know there's some that don't. So just remember, they won't always be yes. Name the vector and write the component form. So make sure you do both of these. This vector, I forgot to tell you this on your assignments I corrected. Some of you, when you did a vector, this was on the assignment where you were given two numbers and you need to draw the vector. So you start wherever you want. This is to the side, so you go 3 to the right and then up 2. Almost everybody drew their vector like this. The vector starts and stops, so the arrow doesn't continue through. The arrow gets to this dot and stops. It's just they put an arrow on there to show that that's where you end up. Okay, so make sure when you do vectors,
It's a
it's
half or...
when you name it, yes.
Oh, wait, we have to... where
So when you name it, this one starts at P and ends at Q because the arrow's at the Q. So you got to put P first, then Q, and then the symbol is like a half arrow like that. Then the component form is how do you get from P to Q? Remember, not a slope. It's side to side, then up and down. It's over 4 and up 1. So go side to side first, then
So
up
we
and
don't put x plus 4 or y plus 1, we just put 4, 1?
down. Yep, component form is written like that. That's the easiest way to write
We're
it.
gonna have to write it otherwise.
No. Here, this is vector mn. So to get from m to n, remember you go side to side first, so it's over 1, 2, 3, 4, and down 2, so negative 2. Reflections. Here, if you could just take your paper and fold it on this line if you wanted to, and then trace it. But the easiest way is you just take each vertex and flip it over at a 90 degree. So you want to go at a 90, and then you just go straight across the same distance away. So you want to go at a 90 and then over the same distance. And then you connect it. This one's a little easier just to sketch. It's just going to be backwards. Just try and get it the same distance away. It's just going to be an arrow that looks like this. So on these, you're always going to start at the same point. You're going to start at 1, negative 3 for each one. So a glide reflection just means you glide it and then reflect it. And they tell you right here what to do. Translated, this means x plus 2 means right 2, and nothing on the y means you don't move it up and down at all. So A just goes right 2, it should be right there. And then you reflect in the x-axis. Here's the x-axis, so it's flipped up over that. 1, 2, 3, 1, 2, 3.
Alrighty then.
Here we start at 1, 3, 1, negative 3. X minus 3 means left 3. Y plus 2 means up 2. So we got to go left 3, up 2. then the line x equals 2 crosses the x-axis at 2. You guys, quiet. So it's 1, 2, 3, 4 away, so 1, 2, 3, 4. Just gotta go off the graph a little bit. Make sure you label them. I forgot to do this one here. After you move it twice, make sure you name it double prime. Did I forget there too? Yeah, I did. So this one, x plus 5 means right 5, y minus 4 is down 4. So way down here would be the first move. The line y equals negative 5 crosses the y-axis at negative 5. So it's 1, 2 away, so you go up 1, 2. So there would be a double prime. Here, x minus 4 is left 4, y plus 3 is up 3.
But doesn't it y equals x? Oh, that's cool.
Yep. So then the line y equals x is the diagonal. It cuts through each square.
Would it be the same if it was x equals y?
Yes. And then the way you do these now is you count diagonally then, because again, it's got to be at a 90 degree. So this is 1.5 diagonals. So go 1.5, it would put it right there. And if you don't see the squares, then just draw in a 90 and then just go about the same distance onto the other side. Okay, name the coordinates of the image after a clockwise rotation. 90 degrees is this way. The full graph isn't there, but C and D are in this quadrant, so when they go 90, they're going to end up down here. B and A are in this quadrant, so a fourth of a turn's up there. So A is down 1 over 3, so you do the opposite. Instead of over 3, you go up 3, and instead of down 1, you go over 1. So A prime's going to end up where C is, at 1 over 3 up. B is down 3 over 3, so it's kind of hard to mess that up because it's the same number. You know it's got to end up over here, so you go over 3, up 3. D also has to go from this quadrant down here. It's just over 1, down 1. So since they're the same, you do the same, down 1 over 1. So there's D prime.
Would it be like that for every 90 degrees, it's just the opposites?
Yeah. And now that you got all 4 of those, you can probably just figure out where the other one's got to go. There's C prime, which would be 1, 2, 3 over, and 1 down. That's it, right?
I overthink that.